Like,
17.
How do you do a y-intercept? That's equal to 0.
these are the points that I saw, right? 221.
Oh, okay, yeah.
221. So I put all these into L1 and all these into L2. Yeah.
Y, that's equal to 0.
So how many guys got the equation of your line done? I got negative 5/6 as a slope. Yeah? It doesn't mean it's right, to be honest. Mine is not right, but it should have been close. It should have been around -1, maybe less than -1. And again, depending on how we drew that, there's a lot of difference of opinions about what looks right. The calculator is the thing that can actually do it exactly right. Ooh for it, right? I picked 2 points. I happened to pick one of them. It was the y-intercept, which is always nice when that happens, right? But if you had to use this equation, it can sometimes get a little gross, but it's just not even algebra, it's just calculations, it's just computations. So hopefully everybody got something roughly around this. -1 maybe. Some of you guys got like a -1 slope, -0.8 slope. I like it. Kick ass. So I wanted to show you a concrete example of what the calculator does. It takes everything you guys have done. If we averaged everybody's together, we probably get pretty close to the right thing. Because some of you guys underdid it, some of you guys overdid it. So what about the part that I'm going to have to see? So everybody hopefully saw what that meant. Get those points and then put them in to L1 and L2. Now here's the part that you have to know how to do. So you hit stat, calc, number 4. So -0.8 is supposed to be the slope. I like it. And almost 19 for the y-intercept, that's cool. And again, when you do it by hand, I'm not going to, oh, you didn't get -0.79. No, you did it by freaking hand. So if you got negative something around 0.8, then you're beautiful. You have -1, that's fine. Is this a strong relationship? Strong correlation? Yeah. How do you know?
Because it's closest to -1.
Close to -1. I love it. 1 would be perfect positive, and -1 is perfect negative. I love it. How would I see these on the screen? How would I plot my data points? Now, if I just hit graph table, I'm going to get some weird shit. There's weird shit in y equals. Make sure y equals is clear. It has some funky ass parabola in there. If I just hit graph now, well, okay, still nothing. Put what? I could, sure. But how do I just see my data points right now? Zoom 9. Let's see if now this happens, that means that I haven't turned my stat plot on. So go to stat plot. Second y equals stat plot. I can turn my stat plot on. If you have your own calculator, you turn it on, you leave it on. So turn it on. It's doing L1, L2, thank God. Now if I hit zoom 9, I should get this. So let me know if you're not able to do that, and you would like to be able to do that, let me know. Hit second y equals to get into stat plot. Kind of makes sense. Make sure that plot 1 is turned on. So you just hit, if it's not turned on, you hit enter, and then just hit enter when you're on top of on. Okay. Now when you hit zoom, and we do zoom 9, because zoom 9 is zoom stat. Well, zoom stat, so it zooms in on my statistics for me, so I don't have to try to find myself. Okay. Cool. Now that should look very much like, it should look exactly like this, because they're the same 3 points. Now how do I get my line of best fit to show up? That's what I put. Now you get y equals. And what was the line of best fit? I forgot already. It's -18.87. Right, hit y equals, and then you can put the equation of the line of best fit in there. Make sure, now here's a little something. There's a negative button and there's a minus button. I want the negative button when I do this, otherwise you get a syntax error. Now watch, real quick, let me go ahead and make that error. I'm going to put a minus button instead. I'm going to hit graph, it's going to say, what the shit? And I say, okay, go to is awesome. Not go ku, sorry. It's go to. And it puts the cursor on the problem. Do you understand? So then I go, oh shit, okay, I need the other, the little tiny negative. I don't need the minus, I need the negative. Now when I hit graph, everybody's happy. That's where the line should have been. I got pretty close. Because you're all like, let me teach this damn thing. What the hell do you want? Again, if I ask you to do this by hand, I'm not going to need you to get it exactly right. But I hope to God nobody would draw it up here, down there. I mean, it's got to make sense. It's got to be the graphical average of all the data points. You should get close. I like it. So is this correlation strong or weak? Strong. It's a decent sized sample, not a huge sample, but it's negative. The R was negative 0.92 or something. Right, when we did the R? Negative 0.924. That's really good. Like TG said, it's really close to negative 1.
So if you didn't graph it and you were just looking at just this, should you know if that's a strong or weak correlation just by the number?
Yeah, if
Positive one?
I take this off and I just look at the plots, why can't I turn you off? You suck. Go away. Good. Okay. If I just look at the points, I should be able to tell that's a pretty good correlation. I mean, it's definitely got a definite trend. They get a little bit away from the line, but not crazy away from the middle of the data points. I should guess that it's negative 0.9 or something around there.
So it's a positive correlation
If the points are going up as you read right
Oh,
to
okay.
left to right. Which country? As you read left to right. But this is going down, so that would be a negative correlation. As one variable increases, the other variable decreases. That's the negative correlation. I like it. Cool. Does that mean that if you study more hours, you will definitely get less mistakes? No. Not from this study. No. Just because we see a relationship between two things does not mean that one affects the other one. That's not what this means. That doesn't mean that this type of study is pointless. This gives me an idea. Then I can construct an experiment that actually analyzes, sort of like testing this difference between two drugs. Then I have to do something to see if it actually has an effect. This is not, I didn't do something to see what effect it had later. I just looked at the way things work at the moment. Do you understand what I'm saying? I didn't take one person, see how many mistakes they made, and then let them study twice as much, and then see, that would be an effect study. This is not a study for effect. This is a study for a relationship. Is there a relationship at all? Is there a point to me looking to see if one causes the other? Yeah, this I would say, oh shit, maybe one does cause the other, and of course, obviously, they should. The whole point of studying is to make less mistakes, right? But we're all human. Okay, so things happen. Okay, how are we doing? Is that decent? Yes.
I just have a question on that. The y equals mx plus b. How did you get the b in this problem?
You mean from my 19?
Yeah. How did you get the 19?
Oh, because I started with it. See it.
So you could just take any y.
You can take the y-intercept if you can get it. Right? That's always a smart thing. Mine just happened to be a whole number. If yours hit between 17 and 19, then it was 18.
So that's the intersection of the b, right?
It's the intersection with the y-axis. That's why it's the y-intercept.
Oh, okay.
Yeah. If it's not a pretty y-intercept, then don't do that. Yes?
I have a question. I just used my 2 points.
Yes, cool. So again, mine just happened to do that for me.
So if it wasn't a pretty number, how would you get it?
Yeah, so somebody tell me, what 2 points did you get? Just 2 points did you get?
Well, I realized I was wrong answer. I got the right answer.
Nita.
I got 2.5, but I realized it should have been 3.
3?
Yeah, and then 17.
17. So you got 3, 17. That sounds right.
And then I put 12.5, but I realized it should have been 13.
13?
And 7.
7. Oh, I see what happened. Okay. I'm with you. Alright, so if I do this, then m would be like 17 minus 7 over 3 minus 13. So you got If you do this, you get negative 10 over, you get 10 over negative 10, you get negative 1.
Yeah.
And then you plug stuff in, y minus y1, so pick a point. So I'm going to pick this one just because. Y minus the y piece equals negative 1 times x minus the x piece. That's all x1 and y1 mean is the x piece and the y piece. Why does it not matter which point I pick? Because both of these points are on the line. So then I just have to clean this up a little bit. Negative x plus 13 plus 7, so I get negative x plus 20. Which is pretty close to what it's supposed to be. What's up? How you guys doing? This is what you call...
Oh, that's when you were saying do it by hand. Because I was saying,
Oh,
Yeah, I know.
I stopped
It just
at the
like-
first step, and then I went ahead and did.
Oh,
how you showed
yeah, you want
us.
to clean this up a little bit so you can see the slope of the y-intercept.
You have to do that before.
Yeah, so you can compare it to the A and the B that the calculator gives us, the slope of the y-intercept. Yep, cool. Okay. Anything else from that little exercise?
You pull up your problem real quick. I'll just use it.
That's good. I just picked the y-intercept. It just happened. The line I drew just happened to go right through 19. So that's perfect. You pick the y-intercept. Why is that better? Because that's b. mx plus b, a nice shorter form equation. This should hopefully be very familiar. This is what you call basic algebra. And yeah, there's a purpose for it. It's not just because I had to do it, so you got to do it now. There's an actual use of it. It's crazy. There's a use for it. Because now I can say, well, what if I studied for 9 hours? Did anybody study for 9 hours in this sample? Negatory. So then I could calculate, I could predict for 9 hours. If I studied for 9 hours, how many mistakes should I make? So I can do negative 5, 6 times 9 plus 19. For my equation, and you guys would use your own equations. Everybody would get a slightly different prediction, but they would all be pretty close if we all drew a decent line. My prediction would be, let's see if I can do this by 15 over 2, which is negative 7.5, so it would be 11.5. I believe. So sure enough, at 9, this goes up to here, roughly 11, almost 11.5, yeah. On my line. So your line might be a little different. Some guys get 11, some guys get 12, whatever. All right, how are we feeling there? I mean, I wanted to give you a concrete example of what the calculator's doing. We did this by hand. Do you understand? We did this by hand. We created this equation by hand. Then we went and said, okay, calculator, show me what you got. And it had this. And that was pretty close to what we got. We're like, what calculator you got close? Or maybe it's right. So why do I trust this to make predictions within this sample? Why do I trust it to make predictions? Why do I trust it? What about this tells me I can trust it? Not because it looks like a trustable thing.
Because the R.
Yeah, the R value is...
It's 9.92.
So it's really close to
-1.
negative 1.
Yeah, or -1.
Which is really close to perfect, right?
Yeah.
All right. So if the R value would have come out to be negative 0.4, I'd be like, I don't think so. Right? I wouldn't trust it. Like I'd plug stuff in and get numbers out, but I wouldn't trust it to be true.
So
I
what
couldn't.
would be the, like...
Well, that's the thing. The cutoff, it depends on how big the sample is. And, there's a little table that you can use that tells you for a sample size what value it's got to be. Right? So, like, I think the sample we did the other day was like 0.456. This is a little bit smaller sample, so it's probably going to be around 0.6. You need to have bigger than 0.6 or, further away from 0 than 0.6. Is that further away from 0? Yes. It's negative 0.9. It's like 0.9 away from 0. So that is evidence of correlation. So I would tell you in a test or a quiz, I would tell you what R has to be bigger than to show evidence. that is related to the Z star versus the Z that you do for hypothesis test, right? There's, depending on your sample size, it says this is how big it has to be, and then we go see how big it is. And that would be evidence of correlation. I like it. Okay, maybe. Please let that chapter be nice. I mean, chapter's so nice. I love it when people are like, why won't you let us use the calculator? Why won't, oh my God, everything's in the calculator. I don't understand the calculator. I'm like, holy shit, which way do you want me to go? So, there it is. Your chance to do everything on the calculator. So, I don't want to hear any shit about it. Alright, so, we are going to get into the chapter we skipped for a little bit. Chapter 11, I believe. Now, the reason I skipped it, a couple reasons. Number one, because 12 is so nice, and it's also very important, the idea of correlation. We hear this all the time, and it's always misunderstood. We say there's a correlation between this and this, so therefore if we reduce this, then these will reduce. No. A correlation doesn't mean that one causes the other. Right? You can't say yes or no to will that cause something to happen. You don't know. All it says is there's a relationship. Right? So this is true. This is a true statement. If teachers get a pay raise, then the amount of booze bought goes up. Does that mean that all teachers are luscious and that we love to drink booze? Well, we do. But does that mean that? No. What happens if teachers get a pay raise? Probably other people got a pay raise. So then generally everything got bought a little bit more. So there was a third thing behind the scenes. It wasn't just teachers getting a pay raise and though they got more booze, so teachers all love booze. It was a third thing. Everybody probably got, or a decent number of people got a pay raise. And then they bought a lot more of everything, including bread and cheese and bologna, whatever. Right? I like that. Because I know what goes in. Alright. So. You will stand up. There you go. Let me put you there. Cool. So, the other reason why I wanted to hold off on chapter 11 is it's a new distribution. So let me try to explain to you why it is needed. So, what governs the shape of this? What shape could this have? I mean, isn't this still normally distributed? Isn't this one still normally distributed? What's the difference between the three of them? No. They're all normal distributions. Why is this one so skinny, and this one's a little bit fatter, and this one's really fat? The spread, which is better known as the standard deviation. So which one would have the smallest standard deviation? The middle one. Because that's the one where everything is closer to its mean. Because what's the standard deviation measure? The average distance from the mean to the data points. Okay. So the standard deviation controls the shape of the normal distribution. Do you understand what I mean when I say that? Okay. What if I want to see what standard deviations look like? What if I were to take a population and start taking samples and then plotting their standard deviations? What does its distribution look like? It's not going to look like this anymore, is it? Because what governed the shape of this was the standard deviation. Shit, so what if I start plotting them? What the hell are they going to look like? Well, they're going to look like this. Big old tail. Big old tail. And the reason reason that is, and this is going to be a hard 0. Because what's the smallest the standard deviation could be? Zero, right? Why is that the smallest it could be? Would a negative spread make any sense? Right? How much peanut butter did you spread on my toast? -3. What the shit? It's a black hole of peanut butter. What the hell? It sucks peanut butter away. You guys understand what I'm saying? So the smallest the spread could be is 0. So that's definitely different, because what was the smallest this could be? How far did this go down? I'm giving you a big hint by... Huh? Negative. Infinity. There it is. Cool. So theoretically, that goes forever. The smallest this could be is 0. Okay. So this is what's called the chi-square distribution.
How do you spell that?
Like that. So it's not chi. It's not chi t.
My brother was in the
Well, there you go. It's delta chi. Right? Not the sigma, but the delta chi. So chi-squared, right? And it's not K-A-I. It's not dragon ball or anything. And for anybody interested, this is what results for degrees of freedom of 1. This is what you get if you fold a z-score on itself. It would actually look very different than this. This is the general look for higher degrees of freedom. That's why it's called a chi-square. It's like the square of a score. So for degrees of freedom 1, it actually ends up being z-squared. It actually looks like this. How do I put this? It looks like if I folded this on itself and multiplied the values together. It's going to be really tall in the middle and then go down, right? Once I get the degrees of freedom going up from 1, it starts to look more like this. So can't I take a sample and have a standard deviation be really big? Isn't that possible? Yeah, that's why this tail goes way up. But normally, if I think a standard deviation isn't going to be close to some amount, is it going to be close to the actual population standard deviation? Right? If I take a standard deviation of a sample, I would expect it to be kind of close to the standard deviation of the whole population. Is that true? So that's what this big middle hump is here. But there's no, it can go pretty far up. It can be very big. If I take a small sample, it can get very big. So that's kind of like why, is this symmetric? Is this distribution symmetric? No. It's skewed to the right. I love it. Looks like Jabba the Hutt. All right. So, the great thing is, I want you to remember, what did we do with this? This thing existed by itself, and then we had several formulas to convert things into z-scores. So I have a z-score distribution that exists by itself. We have a chart that's just the z-score distribution. I can look shit up on it. You with me? It doesn't have to come from something. It just exists. And then I can say, well, what if I have something that follows this distribution? How do I compare them? How do I use it? Well, I can change things into z-scores. If I have x, I can change it into a z-score. Right? If I have p hat, I can change it into a z-score. Or not hats there if you want to. Either way. Wow. Right. So these are formulas to convert observations or things we're working with into scores that I can then see where they fall on this picture. That's what we've been doing a big chunk of the time in this class. So now I'm going to have formulas to convert observations that I see into chi-square scores that I can then see where they fall on this picture. And it shouldn't surprise you that I'm going to have a chart of values that I can use the same way we did with the z-score. Is it going to be the same as the z-score? No, it doesn't look a damn thing like that, really. It looks very different. It's not symmetric either. That sucks. Because over here was great. If I knew this was 1.9, this is probably negative 1.9 for making confidence intervals and all that kind of shit, right? It's beautiful. Symmetric. Yay. Not symmetric. 0 is here, not in the middle. Shit. All right, so you're going to see that in the chart that I'm going to give out to you. which I'll do probably right now. Let's see. Stay there, Jimmy. So you'll notice something familiar on there, hopefully. What do you see on there that's familiar? Yeah, good. Degrees of freedom is on there, right? Everything else basically is unfamiliar. So let's talk about how to use this first, and then we'll do our first little use of a chi-squared chart. So chi-squares are normally, one big use of them is for investigating how standard deviations are spread out, but that's a later section in chapter 11. I want to start with the slightly easier, less freaky use of it, which is called the goodness of fit. That sounds nice, right? It sounds like the best fit line. But very first thing I want to do is see how to read this chart. What really, really sucks about this chart is these are the areas on the top. These are the areas to the right of the score, right? So remember the z-score chart always shows the area to the left. So we did this just to screw you guys over. I don't know why they did this, to be honest. So if I had a sample size, let's say I have a sample size of 7. And I want, let's say I'm checking, I got a right tail test. Let's make it left right now. Left tail with 0.05 in it. So it'll be left tail, 0.05. So what am I going to, how am I going to find this value here? I have to know the area to the right. I like it. It'll take a little getting used to, but we've done enough of these kind of charts. It should be a little bit quicker to pick up on this. What's the area to the right of this then? I want this score right here. I want to know what that score is. I know it's a chi-square score because I'm going to get it off of the chi-square chart. It would be a z-score if I was using the z-chart. It's crazy. So what area am I going to actually look up? 0.95. And what's my degrees of freedom? 6. So if we look at 0.95, degrees of freedom is 6. I get 1.635. Alright, so that's how you read this. The thing that's a little bit evil is it's to the right of the value where you're really used to it being to the left. But we just got to remind ourselves that's what it is. I can make confidence intervals with this thing. So let me ask you this. So we could create confidence intervals for standard deviations the same way we did for means. So I can find an S and then say we are 95% confident that the real standard deviation of the population sigma is from this to this, the same way we did with confidence intervals for the mean, for the proportion, the exact same way. Because what's one big thing this thing does is it tells me how sigma is distributed. So if I wanted to find, let's say the What you got, Jeff? 99% confidence interval. And I know that N is 21. What would these two be? And I normally call this one chi-square small and chi-square big. So we help you out a little bit. For the chi-square big, what's the area to the right of it? 99% is in here, so how much is outside? 1%, so how much is on that side? 0.5% or 0.005. Now here's something that's kind of cool. Here's 0.005 there. Right? There's also 0.005 here. So what's to the right of this one? What's to the right of this one? 0.995. And notice how they're symmetric to each other on the chart, right? So if I wanted this, it would be this. If I wanted this, it would be this for the other side. That's really kind of nice. I don't know if you guys notice what I'm trying to tell you. No? Okay. So everybody cool with the fact that there's 0.005 there? We got to be used to that. 1% outside, so there must be 0.5% on either side. That's 0.005 in decimal speak. Yes?
It says it's still one tail, it's not two tails.
It's a confidence interval. Confidence intervals are always two tails. Because I'm chopping it like that. But the one or two tail doesn't even matter for this sucker. Do you see that?
Yeah.
It's not set up that way. Yeah.
So that one side would be 39.9.
Yeah, let's see. So degrees of freedom is 20. So 0.005, stop at 20, which would be 39.997. That's chi-square big. Chi-square small.
7.434.
Yeah, 0.995 is going to be 20, but on the opposite side, 7.434. So just to really hammer this home, what if I had the same setup, same degrees of freedom, but I want the 90% confidence interval. So what percentage is out here now? 5%, so 0.05. And what percentage is above this one? 0.95. So look at, here's 0.05, right? 0.05? And there's 0.95. One in, one in. I mean, they're symmetric from each other. That's beautiful. Whenever you're trying to find two sides of a chi-square confidence interval, they're going to be symmetric in the chart. Let that be nice. That's 0.05 for damn sure, right? 90%, there must be 5% over here. So 0.05, stop at 20, bam, 31.410. What's the other one going to be? Symmetric on the other side. 95%, 10.851. What did I say over there? 31.410. You poor guys got none of that. Yeah, so 31.410, that's degrees of freedom of 20. 0.05 is in that tail. Over here, symmetric in the middle is going to be 95% to the right of the other tail. That's going to be chi-square, what I call chi-square small. Yes, sir?
So if it's 90%, why are we looking at 95?
Because that's 90% in the middle. This is to the right of the value I want. I want this value. What's to the right of it? 90 plus 5. Yeah. So the confidence interval percentage can never be included. I mean, I can't just look at that alone. Because the charts we use talk about totally that way, or totally this way. Yeah. like it. So that's how you read the chart. That's the important first step. So now let's talk about how can we use this chart now. Besides to make paper airplanes or start fires. So let me do a couple examples with you. Of what's called the goodness of fit test. Let's see if we have a decent example. Oh, here we go. This would be good. Yeah, sure. Let's say that I expect. I just got an idea from the homework. I expect grades to be distributed the following way. I expect, I expect to have 15% A's, 25% B's, 30% C's. What do we got here? 35, 70, 20% D's, 10% F's, 30, 60, 85. Yay, Jeff. Alright, so let's just say there's a teacher or there's an organization that thinks this is the way that grades should be distributed, which actually is the way it sometimes happens, and I kind of laugh at it because I'm like, it all depends on what students I get. Really? Don't you realize? But anyway, so this is kind of the way they expect it. And let's say, so this is the way this is going to work. This is the goodness of fit. So let's say my observed grades, one semester, observed, the grades that they actually made, let's say that out of 80 students, let's say that 7 made an A, 11 made a B, 14 made a C. How many do I have left? 18, 32. Oh, maybe I want to make this a little higher. Let's say 24 got a C, 35, 42, 38. Let's say that, let's say 28 got a D, that's bad. And then 10 got an F. That should add back up to 80, hopefully. 18, 42, 52, 8. Okay. So just on the surface of it, do you see how it doesn't follow this exactly, but it sort of follows it a little bit. So the whole point of this is it's sort of, the nice thing is it's going to be a lot simpler than a hypothesis test. But it sort of has the same thing at heart. It says, is this evidence that it didn't follow this pattern? So what would happen, what do I want to check, what would happen if it followed it perfectly? What would happen if it followed it perfectly? So I have 80 students. What should have happened? What would I expect to have happened if it followed this perfectly? Somebody help me out. How many A's should there have been?
15% of 80.
15% of 80.
12.
12. I like it. One more color. Yay. So there's 80, so there's 12 is what I would expect to see there. B's, 1/4 to 80. 20. C's, 30% of 80. 24, so I got that many. But then D's is only supposed to be 20%. 16. And then F's 10% of 80 is just 8. I like it. And just to make sure these add up to be 20, 40, 64, 80. I like it. I'm going to stop there for a second. Have I done anything that's really, 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 not even that many reals? Have I done anything hard? Yeah. They're going to give me this. They're going to give me this. You have to calculate what you expect. What number would I change that would change all these numbers? Yeah, exactly. If I had more students, I would expect more of each. I just take the percentages of that much. Okay. So, this is related to hypothesis test. Would you say that 7 is very far away from 20? See, people have done this a lot would say, I can't say because you haven't told me what the average distance is. So what if I told you the standard deviation is 400? Is 7 very far away from 20? No, because the average distance away is 400. So 7 is not very far away from it. What if I tell you the standard deviation is 1? Then yes, they okay, good. I like it. So that same problem we have without more information I can't tell, you would say, well, that's really different. Is it different enough? That's the question. To be evidence that doesn't follow this. Stop there for a second. This is a sample of students. So is it evidence that I don't follow the suggested grade distribution? I don't know. We've got to do a test to figure it out. We don't have a test that would really work for this. Now we do. So here's the equivalent of this. The equivalent of that. And this is on page, I don't know if you're following along. Oh shoot, I'm way in the back. Well, it's on page, I'm just in 11.2. Page 583. And then what the O and the E means is exactly the words I use here. There's observed and expected. So what I'm really trying to do, let me get you the overall outline. The way that the goodness of fit test works, and what I haven't told you yet is at what level do I want to test this? The alpha equal 0.5 and 0.01, and oh shit, would you like that? Right, so the way this is going to work is, am I far enough away from 0? So what would it be if it was perfectly following this? What would these be? These would be 12, 20. So what would I get when I took the difference between these? Zeros. So then it would be 0. So really I want to say, is it far enough away from 0 to be evidence that they are different enough? It's very familiar, very similar to hypothesis test. Notice there's not as many steps. That's good. All right. So how do I calculate this from here? And then we'll talk about how to get the benchmark to compare it to. Well, what does this tell me I have to get? If I cover this, I've got to get that. So first I have to subtract these, then square them, and then divide by the expected, right? So take a minute and try to do that. If you haven't already copied this down, you should. You just put an E, an O, and then that. Do I have that? Yeah. Oh yeah, it was on the other side here. That's right. Okay. Yep. So if you want to, just reminding us. Some of you guys might be doing this. You can use your calculator. So here's your expected 12. 8. Here's your observed. 7, 11, 24, 28, 10. And then here's your L3 is going to be, to put the whole thing in there at once. L3 is going to equal observed, which is for me right now is in L2, minus expected L1 squared. Is everybody with me here? Observed minus expected, L2 minus L1 squared. Divided by expected, which for me again is in L1. And then you just have to sum those up. 2.083 forever. 4.05. 0. 9.5. And the 0, of course, makes sense because we hit that target exactly, right, for the C's. Just go ahead and call this chi-square critical, like they do. Chi-square star is just kind of putting a lot of stuff up to the x1. It's kind of weird. So what do you guys get when you add those up?
Can you add them up?
Yep. It's 15.6.
Yeah.
So that's like Z star. This is what we did based on our observations. That's like Z star. You guys semi with me. Even if you hated hypothesis tests, you still did enough of them that you're like, okay, that's what we calculate. So I'm sort of doing this a little out of order, but that's all right. Yeah.
What's this here?
See it?
What's C again?
Oh, so I'm doing like the book that critical. So they call this the critical score. So it's like my Z star. I just figure making chi-square stars is like too much shit up there. Yeah. Now I want to know. Let me take a step back. We sort of did this out of order, right? We saw how far away we are. We're 15.633. Is that far enough away from 0? It's definitely not 0. There's definitely a difference, and we know there's a difference between these two. It's a question of, is that difference big enough? So now let's say it's at alpha equal to let's say 0.05. Why that's the most used one. How many tail test is this? It's always going to be a one-tail test for goodness of fit. It's just strictly, are you far enough away from 0? It's always going to be up here. So alpha is always going to be that. That's kind of nice. Now here's the thing you don't know. Here's the new thing. This is a very new thing. What the hell is the degrees of freedom? Not 79. N, for goodness of fit, is always the number of categories. Number of categories. And how many categories were there? 5. So N minus 1, 4. So look at the chart. Degrees of freedom of 4. 0.05 to the right. Stop over there, Jeff. There it is. 9.488. So did we find evidence? That's how far we have to be. So if we get in here, that's evidence that they are different. Did we find evidence that they're different? How far did we make it? What was our chi-square score, guys? What was it? It was 50. Did we make it far enough away? We're way the shit up there, right? We're way up there. So did we make it far enough away? Yes. Why not? Oh, you got to switch around. This is our benchmark. I just kind of did it out of order. I wanted us to use a formula first and then go back. This is how far we got to make it. What is this number based on? The level of significance, right? And the degrees of freedom. This is how far we got to make it. How far did our sample make it? 15.6. Way the hell up there. So this would mean what? What would it mean if I got 0? That would mean that these are the same. So that would mean it would follow this pattern exactly. The further I am away from 0, that means the more different these are. Do you see why it's called goodness of fit? Does this fit this pattern? No. We showed evidence that is way the shit out there. It's way different than that pattern. It's different enough. So that's evidence that my grades do not follow this pattern. That's how you would answer this. No, these grades do not follow this pattern. Yes?
So it would have to be exactly 9.
No. Anything below this.
Oh, below it.
Yeah. 0 means no difference. Anything in here means not big enough difference. When does it start to be a big enough difference? There. So anything that and beyond is a big enough difference to say that there is actually a difference. Yeah.
For alpha, did you always use 0.05?
No, it'll tell you.
Oh, we'll tell us.
If it doesn't say, then you use, that's the most used one, is 0.05.
Okay.
Just in case, I can't remember if there's some that they leave it blank. Because somewhere in the book they say that 0.05 is the most used one. Yeah. Alright, let me give you this handout here. Oh, you already got this handout. Keep forgetting. Side 2. Turn it to side 2. I got another worked out example up top. I want you to realize the difference here. How did I fill in the expected column? So read through that first example, the one about the M&Ms. Read through that. Okay. Should have read through it by now. So it's very obvious how I got the observed ones. I have to tell you that. There were 5 brown, 6 yellow, so forth. Cool. How the hell did I get 7s in the expected? Yeah, because I'm checking to see if it's uniformly distributed. So I wanted to have the same number of M&Ms in every category. Why wasn't that one the same? Because I wanted to follow that non-uniform. It was based on the percentages, which is a lot like the example I want you to do right now. Number 2. So try out number 2. And on number 2, I do tell you it's the alpha 0.01, in case you missed that.